Hello and welcome back. It's been a while. Here is a little intro of why and what I'm planning to build in this video. You see, this is a piece of kinetic art which I'm currently working on, or should I say the last 8 months, because it's very time consuming. And here is the thing. As you may have already seen, some of the body parts are made of styrofoam, very dense styrofoam here. You can see, and you can imagine what kind of mess it makes to shape this styrofoam with a knife and a saw and a rasp and whatnot. So in this video I want to build a hot wire cutter to cut styrofoam, big styrofoam blocks. It is on the agenda for quite a while now, and finally I have the time and I'm in the mood to start the project. So follow me along to build the hot wire cutter for styrofoam. And here are the requirements. The foam panels come in packages like this. The panels are 1 meter long by half a meter wide, and they are available in different thicknesses. And ideally I want to be able to cut one full block like this on the wire cutter without opening the wrap foil here. So that's the game plan. Building a machine which is big enough to cut a block like this, at least in this dimension here, so half a meter. And as usual, every machine build starts with a solid base frame. In this case I want to build the base out of these old base frames from a never finished workbench project. Uh-oh, my machine needs some TLC. Joe? 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 quick stop, because I'm pretty sure you're getting what I'm doing here. Two of the legs are shorter than the other two. The reason is, on these two legs I have rubber bumpers or rubber feet screwed in, and the other legs work together with these casters here. So overall I will have the same height of the table. No rocket science. It's a proven concept which I use many times on my homemade machines here. It works, and I'm doing it again on this machine base here. Two. Woohoo! Round stock is by far not the best choice, but hey, that's what I have. And that's how I usually do these things. I start with one side, aligning everything with my square here and my magnets, and try to avoid as much warpage and weld distortion as I can. And once one side is done, I flip the piece over and tack weld the other side, and pulling the pieces into square and where they belong to be. And after checking it again, if everything is square and not warped in any direction, I will do all the finishing welds. And of course I will spare you watching me grinding all these nasty flux core welds. So after the grinding it looks like this. Ugly as hell, but it could have gone much worse. Coffee break. Joe. Alright, so the project was quite simple up to this point, because yeah, let's face it, it is just a table base. But now comes the fun part, making or finding the bow which holds the cutting wire. And I think I may have something laying around on the scrap pile. Never seen on YouTube? Welcome to our private junkyard. Or should I say, the property as a whole is a junkyard. And this thing here is what I am after. It is a part of an old oil tank, and it should be about the right size to do the job. Junkyard. All the way out here. Alright, that's the flange for the bow or boom, if you prefer, because I like to have it detachable for transport and repairs. And the boom is what I'm going to fabricate next. Yeah, welding socks on, full steam ahead. Yep, so that's what the part looks like after cleaning all the welds with various methods, including my trusty die grinder here. Overkill? Maybe, but why not? I can. Voila! It fits right away. But obviously this pipe here is way too long and I need to shorten it like so. Okay, now I have two options. Option number one, which will be the easier way, is to make a fixed mounting point for the cutting wire, which means I can only cut 90 degrees. Or option number two, I make some kind of slider here, where I can move the upper mounting point of the cutting wire to give me the option of cutting the stock in any angle I want. So basically it should mimic the blade tilt of a bandsaw or table saw, and I think that's what I'm going to do. I will make a sliding mechanism here, and I already found something in my stockpile here. It is a DIN rail. The electricians in the audience will probably know these things. And just as a coincidence, these rails here fit perfect over the DIN rail. Just as luck will have it, and that's what I I'm going to use for the sliding mechanism. The DIN rail is mounted to the boom, and this part is my sliding mechanism. I hope all of this makes sense. If not, you will see in a minute. Alright, so you may wonder what this guy is doing. Let me explain. This is our slider, the carriage on which the cutting wire will be mounted. It has a riv nut pressed into it so that I can lock the slider in any position I want. Okay, that's locking. And to connect the actual cutting wire, I made these things here. They are made from a very tough floor tile material. It's not ceramic. It is what we in Germany call Feinsteinzeug, which means sintered stone. This is very tough to drill into. I drilled the hole underwater in a water reservoir, and they are meant to get bolted on like this here on the slider, and then another bolt which is made from brass fits into here, and I can connect the cutting wire to this brass bolt. Why am I doing that? See, I don't want to have the low voltage DC in contact with the chassis ground of the machine, because chassis ground is only protective earth and nothing else. That's what I want. So that's why I have these insulators here to electrically isolate the protective earth from the DC low voltage for the cutting wire. I hope that makes sense, but this will be the same under the table, but without this sliding mechanism. Okay, so the slider works as it should, and to better demonstrate you guys so that you can see what I mean, I attached a piece of red cable here to the bolt, which is too long at the moment, but I can shorten it at any time. So once I slide this back, I can adjust the cutting angle of the cutting wire, but this creates another problem. If I slide this to the far end, the cable gets longer and longer, of course, so I need something to stretch the cutting wire. Some kind of, I don't know, teeter-totter system. But yeah, happy with the result so far. Next up, wire tensioner. Daylight is fading, so I had to speed things up quite a bit, and I did some work off camera, but I think you get the idea what I'm doing here. This is my cutting wire tensioning contraption. Here is the cutting wire, and this part here is hinged, and I can put weight on it to tension the cutting wire even more. I think I will put the transformer on top of here. I'm not sure yet. So when I slide here my cutting wire, it moves up and down. There will be a ceramic insert in the table so that the wire can touch the table here without burning it. Next step is to make yet another slider, a smaller one. Same system, rinse and repeat. And this slider is to take care of the side-to-side adjustability here. Well, guys, for some reason I was not able to pull a cable through here. I don't know why, it got stuck somewhere here. So what I did is I added another steel pipe here, which will act as a conduit to pull my cable through. It also helps with the stability issues I had. Now it's way strong enough, and I cleaned everything firmly, and now I think it is time for the first coat of paint, at least for the bigger parts. Schmatze. I said this many times before in my videos. Even though I don't like painting, I'm very much enjoying it, seeing a product shining in its final glory here. That's how I like it. Next up, electronics. And to be honest, I have no idea how to go about. Alright, so I dug through my storage shelves here, and what I found was this. It is an industrial grade transformer, 230 volt line voltage in, 24 volts out, 100 watts. And considering its ruggedness, I would prefer to use this heavy transformer here in my machine, if it is powerful enough. I did some calculations, and to heat up the 80 centimeters of cutting wire I need at least 40 to 50 watts of power, so 100 watt is plenty enough. So I will go with this transformer here. So here is my test setup. I have my transformer, 24 volts, 100 watt, hooked up to mains voltage. At the moment we are drawing 22 watts. The AC goes via these cables here to the bridge rectifier here, 50 amps bridge rectifier on the heatsink. The DC plus minus about 27-28 volts goes into this bank of power transistors. These are MOSFETs, way too many of them, but it's just for doing some tests here. And the gate of the MOSFETs is connected to my trusty PWM generator here. Currently we are running on 1 kilohertz at 24% duty cycle. And let's try. I have my cutting wire here spaced 80 centimeters apart, so about the same distance as it would be in the final machine. And we can already cut, but oops, slowly. Now let's increase the duty cycle to, let's say, 50% or 40 for the moment. 40%. 31 watts. Let's try again. Yeah, now it's cutting fine. Still a bit on the cold side here, but it works. Let's go to, let's say, 55%. $39 watts, shy of 40 watts, and the wire is humming, which I, to be honest, like. And now it's cutting fine, absolutely fine. So I would say this transformer, 100 watts, is powerful enough to do the job. We are running it at the moment at 40 watts, so there is plenty of oomph left. And here 55%, so also plenty of power left on the PWM controller. Everything is still stone cold, of course, and yeah. Ooh, great. Perfect. let's build a circuit. Quick stop along the way. So this is the rough idea of the circuit which I want to use. It is based on the NE555 timer IC, and I designed it in a way that the frequency of the PWM signal is fixed at the moment to 260 Hertz, and I can adjust the duty cycle, of course. That's what it's all about here. And here is my breadboard design, and it already works. I can adjust the duty cycle here, and by changing the timing capacitor, this one here, I can alter the frequency of the hum or of the beeping noise which the cutting wire in the end should make. As I said, I like the feature. Yeah, that's why I want to use it on a header pin here, so that I can change it if I don't like the tone it makes, pitch of the tone. So yeah, PWM works. I will build the actual PCB mostly off camera, because the video is getting already too long. So I will be back once most of it is done. Here are all the electronic components of the machine laying on the table. Let's start with the power cord, 230 volt AC, Europe standard. The AC, the mains, comes in through a mains switch. Maybe I will use a double pole switch, like drawn here in the schematics. This is the main switch to turn the machine on. Then we have the powerhouse, our big transformer, 230 volts to 24 volts AC, 100 watt. The mains goes via a fuse to this big transformer. The 24 volt AC goes to a bridge rectifier. Here, 25 amp bridge rectifier, to a smoothing capacitor, 10,000 microfarad, 100 volt electrolytic capacitor, which will give us roughly 36 volt DC here on the power rail here for the cutting action, and the 36 volt will be switched by 3 MOSFETs, N-channel MOSFETs, to the heating element, which is in this case our cutting wire, 304 stainless steel, 0.3 millimeter in diameter. If you need a hotter wire, go for a thicker wire like 0.5 or even thicker. So that's the heavy lifting here. And here comes the control unit, which I already finished. This is the finished circuit board, and yes, it has its own power supply. That's how I build stuff. So let me quickly go over what's going on here on the circuit board. You see on the circuit diagram we have again another main transformer, a auxiliary transformer, a smaller one, again with a fuse. Here mains comes in here, goes via the fuse to a small mains transformer. The 12 volt AC from this transformer goes through a bridge rectifier here on the circuit board to a bulk capacitor, this one here, 47 microfarads. So we get around 16 volt DC here. The 16 volts feed into a 7812 7812 voltage regulator here. The thing here on the small heatsink, again with its capacitor 1000 microfarad, so we have a stabilized 12 volt power supply for the chip. The timing IC is a classic NE555 timer, and I made the circuit in a way that as I said before, that the frequency of the PWM stays roughly the same. Here I have my potentiometer, there it is, to adjust the duty cycle. Here is the timing capacitor, which I can change if I don't like the tone which will be created by the cutting wire. Okay, disconnect the capacitor here and put another one in if I don't like the pitch. Here is our NE555, the two diodes here, another capacitor to smooth out the voltage on the control voltage pin. Very important, most people forget to put it in. And the output of the chip goes to a LED, control LED, which is this yellow one here, just to show me if the timing IC is working. And then I have a Schottky diode here with a low voltage drop of less than 0.3 volts. This is, where is it? This is this diode here. It's just a safety measure, and just in case if something goes wrong here with the MOSFETs, the 24, or should I say 36 volt, cannot come back into my chip here. Current limiting resistor 150 ohm. Theoretically you wouldn't need that, but yeah, it's good to have. So the three MOSFETs are all hooked up in parallel here on my heatsink. Theoretically one should do the job just fine, but I've chosen to use three of them. They are all in parallel, so here are all the gates connected to our chip. Have a gate pull down resistor 12K, and source and drain are connected to our ground here and to the heater. And yes, I have a flyback diode, which is this one here, because the cutting wire, I'm pretty sure, has some inductance to it, so it's a safer option to have the flyback diode in circuit. Yeah, that's basically it. I mean, it's very textbook. There's not a lot to it. This is our heating power section here. This is our control section. I will post the circuit diagram onto my Pinterest profile as well as to my Patreon profile, just in case you want to copy the design here. Other than that, that's all there is to it. Now I need to fabricate a enclosure, and the assembling process is also in full swing here while I'm working on the electronics. Nice. Woo! So it's definitely not a masterpiece, but it will suffice. Here is my mains cable coming in, mains fuse, circuit board with the MOSFETs, power transformer, bridge rectifier. I'm not using a heatsink. I use this metal plate here as a heatsink. Mains switch, double pole, mains power indicator, and the knob for the potentiometer for the heat adjustment. And this thing goes over like so and sits under the table. Yep, the electronics are finished and working. So all the electric stuff is completely done now, and the controls are well protected here inside the base frame. Now obviously I cannot use the machine without a proper tabletop, and that's what I'm going to build next. So guys, this is the material for the tabletop. It is melamine coated particle board. Cheap stuff, but it is smooth, so I will use it. And this is the table insert where the cutting wire passes through. It is a wall tile, ceramic wall tile. So next up, cutting these boards to size, put edge banding on and making the recess for the ceramic insert. A replaceable table insert. Always nice to have. I have it on each and every of my machines. I made the recess with my planche router here, redneck style, freehand. That's good enough for me, and I had to do it outdoor because I'm working on a furniture project here, wet paint. Yeah, okay, table insert is done. Next up is the hinged table extension. Oh boy, it was so hard to film under the table, so I had to turn things over anyway. So this is the underside of the tabletop. This is the extension here, hinged here, and here I have plates, locking plates I call them, with a hole in the middle here. And these holes correspond with these bolts here. So the heads of these bolts lock into these holes, or they should at least, so that I can lock these wings here in place and adjust the height of the table if it decides to sag. And I riveted these hinges here to my table leg here. Okay, fold everything back. That's the basic idea. No rocket science again. Just a folding table. Yeah, now it's time to put everything together, and let's see if I have carriage bolts, short ones. Maybe. Here is the game plan. Since I don't have enough carriage bolts laying around, I will use the carriage bolts for the lower shelf here, and these countersink bolts here for the tabletop. Alright, the tabletop is firmly attached with these countersink screws here, as well as the shelf. And I also attached a chain here to lock the swing in place when the machine is not in use, because this wire turned out to be very delicate and easy to snap. So that's the tabletop done. The only thing left basically is to make a rib fence, and off camera I already prepared something here. These are basically 2 pieces of angle iron. They will be attached to the machine base like so. And I have this clamp type of thingy here, also the same angle iron. I can hook this over and lock it. It's the same system as on many of my other machines. Here, it even fits on this one. Oh, it's a proven concept. It's simple enough, it works. So I did the same on this machine. Next up, bolting this rail here onto the machine base, and yeah, finding something what I can use as a fence, like a, I don't know, an aluminum rail or something. And because I had some questions in the past, yes, these are countersink riv nuts. So when they are pressed in, they are absolutely flush with the surface. Yoo-hoo! Now comes the fun part. One thing for sure, you need practice. But that's fun. That's fun. But I have to say, you need definitely a lot of practice to get a nice finish. The finish with the fence is perfect. I'm not sure if you can hear the tone. Maybe. I can hear it. Wait. I would say that's a success. And I say thanks for watching.